Hey guys, we're starting chapter 17. Some of this is going to be reviewed from chapter 16, but we're going to be applying it in a slightly different way. So here we go. As we learned in chapter 16, what do we call things that are malleable? Remember, that means they can be hammered and shaped. Ductile, they can be stretched out into wires. Lustrous, they're shiny and conduct heat and electricity. Well, those are our metals. So this chapter is all about what do those elements do. Like last chapter we learned about the periodic table a little bit, what metals are, non-metals and stuff. But now, what can they do? Why do we categorize them like that? So metals in particular can form two different kinds of bonds. And it depends on what the other element is that they are bonding with. Okay? So if we have a metal bonding to a non-metal, it's going to form what's called an ionic bond. And we're going to talk a little bit about what an ion is. But if you have a metal bonding to just metals, it has a very unclever name, metallic bond. Okay, so now a little more about that first kind of bond we said metals can form, which is the ionic bonds. So what are ions? Okay, so ions are any particle that have a charge. Okay, notice in that definition we don't say a positive charge or a negative charge, just a charge. So we can have positively charged ions or we can have negatively charged ions. They are still called ions. So how would something gain a charge? How would it become an ion? Okay, so it would become an ion when it gives electrons, I guess electron or electrons, to another. Okay, so remember electrons are negative, right? So if you are a neutral atom and you gain an electron, okay, you're going to become a negative ion because you have gained negativity. Okay, so the opposite is also true. If you were neutral and gave away an electron, electrons are negative. If you lose negativity, like in math, if you subtract a negative, right, your value goes up. So if you gave away an electron, you become the positive ion. So the atom giving away electrons becomes positive, and the atom receiving electrons becomes negative. So you probably are familiar with the saying that opposites attract. Well, that comes from this idea with charges. Okay, so when we're talking about, well, what is an ionic bond? It's really that attraction between a positive ion and a negative ion because opposites attract. Okay, so as something is held together with an ionic bond, it means one of them's positively charged, one of them's negatively charged, and those oppositely charged things are pulled towards each other. Okay, metals, remember we're under the heading of metals on this page, will always give away electrons when they are forming an ionic bond. Okay, so they will always become positive while their bonding partner, nonmetals, tend to gain electrons and become negative. So let's look at this picture down here at the bottom of the page and see if that makes sense. Remember last chapter we had those dot diagrams? Well, here they are, right? They're back. Okay, so here's sodium. It has one dot. That stands for its one valence electron. Remember, you're going to see our periodic table. It's in group 1. So that was our clue. It should have one valence electron. There's its one valence electron. Here's chlorine. It is in group 17 or 7A. So we know it must have 7 valence electrons. So there's its 7 dots. Okay. We also learned, again in the last chapter, things are stable with either a full outer shell of electrons or 8 valence electrons. Okay, So if sodium gives away an electron, its now outer shell is the one inside the one it was before, and it's full. If chlorine has 7 and it gains 1, it will now have 8. So after sodium gives away an electron and chlorine takes it, they are both more stable. So this electron is going to be transferred. Okay, so we end up now sodium here, you see it's plus, chlorine's negative, so we have this opposite charges attract, which is an ionic bond. Okay, ooh, got a little crooked there. So there is the first kind of bond that metals can form. All right. So, second type of bond metals can form was metallic bonds. We would say metallic bonding occurs because metals have a weak pull on their valence electrons. Okay, so remember, this is when they're bonding metal to metal, metal to another metal. Okay, so we said metals always would rather give away their electrons. So you can't give away electrons to an atom that doesn't want them, right? So instead, they kind of just like let them run around loose and shared between all of the atoms. So the valence electrons can move throughout the substance, and we call them the sea of electrons. Okay, and they picked that name for a reason, just like with water, right, that we always think of water as kind of flowing and moving. And the same is true of those valence electrons. So in a group 1 metal, remember they each would have 1 valence electron. So for every atom here, we have 1 valence electron, but they can move around. Okay, so this one might be moving over here, this one's over here, this one's over here. They don't stay with their atom. Okay, but we have this overall kind of negative sea of electron pulling on the positive atoms and holding them together. Group 2. Okay, so group 2, each nucleus would have 2 valence electrons. And again, the idea is these valence electrons are loose. They can move around. They are the sea of electrons. Okay, so this explains another interesting property of metals, which is conductivity. And I just realized that's not actually what I want to put there. I want to put electricity. Okay, so electricity, as we know it, is the flow of electrons. Okay, so these electrons clearly could very easily flow. Okay, so that explains the conductivity. That's literally what conductivity creates, is the ability for electrons to flow. That's electricity. All right, so those are the two kinds of bonds metals can form, and we do put metals into a few categories here. So we have the first group are called alkali metals. Okay, they are in group 1A, or some periodic tables just call it group 1 of the periodic table. These are the ones like sodium. They have 1 valence electrons. It makes them extremely reactive. And there's nowhere on Earth you could go to find any of these metals in their pure form. Okay, so let's look at some of these examples here. So group 1 are going to be these metals here: lithium, sodium, potassium, rubidium, cesium, francium. Okay, so there's nowhere I could go and find a deposit of pure sodium underground or pure potassium. Well, you're like, well, I get sodium in my diet every day, Miss Fees, you're crazy. But you're not intaking pure sodium, right? You're probably intaking salt, which is sodium chloride, which is a compound. Okay, so you're not going to find these anywhere on Earth because they are so reactive. Okay, they're very unstable by themselves, so they've always kind of been reacted by the time anybody would found them. So each alkali metal has only 1 valence electron. If it loses this one, it becomes more stable, since we'll have the same number of electrons as a noble gas. Okay, we're going to talk about these noble gases till we're blue in the face, but just kind of a preview here. These are the noble gases, the very, very far right group, and they're extremely stable. Every single one of them has a number of electrons that is stable. They don't react. Everybody wants to be like a noble gas. So when an alkali metal loses their 1 valence electrons, their charge is going to be positive 1. All right, second group are the alkaline earth metals. And they are in group 2A, or your periodic table might just say 2. And they are also quite reactive, slightly less reactive than alkali metals. And they're also not found in a pure state on Earth. So let's look at some of these guys. Okay, so we have beryllium, magnesium, calcium, strontium, barium, radium. So again, you might be thinking, well, calcium, it makes my bones. Nope, your bones are made out of the compound calcium phosphate. So you're not finding a deposit of pure calcium. You can find things that have a lot of calcium in compounds with other elements. Okay, so let's think about this. Each alkaline earth metal has 2 valence electrons. So to become like a noble gas, to become stable, it's going to lose 2 negatives. If I was neutral and I lose -2, my charge is going to be positive 2, right? Okay, so one other thing about these, if you didn't watch the video where they exploded the alkali metals, it'd be a pretty, pretty cool video. If you Google Brainiac alkali metals, oops. It's like a 5-minute video. I linked it when we were learning about metals last chapter, so just look for it if you didn't watch it. It's pretty good. All right, last page today. We have what are called transition metals. Okay, and notice I didn't give you one group for these. Okay. So they are in what I'm going to call the middle groups. Okay, or you could say, if you wanted to, 3 through 12. Or 3B through 12B, depending on your periodic table. These are less reactive. Okay, so these are ones that you might be able to find in a pure state because they're not super reactive. They're already kind of stable. Okay, so they may be stable alone, but also form lots of compounds. So they can kind of bond or not bond. They're kind of stable either way. Okay, often these metals have different colors depending on their charge or bonding status. So think about one you're probably familiar with is iron, right here. Okay, so iron, pure iron, is kind of like dark gray, but if it becomes positively charged and forms iron oxide, that's rust, it becomes kind of that reddish brown color. Okay, so the color of that ion is different than the color when it wasn't charged. And another example, chromium gives rubies and emeralds their color, and rubies are red and emeralds are green, but it just depends on what the charge on chromium is, right? It could be +2, +3, +4, depending on how many electrons it gives away, and that also determines what color it appears to us. Same idea, Statue of Liberty is made of copper. Okay, if you look up a picture of the Statue of Liberty, it does not look copper colored, right? It looks kind of like greenish, like a seafoam green, because the copper reacted with the oxygen and the water and became copper oxide, which is a different color. So again, those transition metals tend to have different colors depending on who they're bonded with. All right, then we have iron, cobalt, and nickel are all there in a row on the periodic table. Here we start with iron, and then just right in a row, iron, cobalt, nickel. They are called the iron triad, and they are the only elements that naturally are magnetic. Okay, there's some other metals that they can kind of make magnetic, but those are the only naturally magnetic elements. And here, if you're thinking, well, what about steel? Remember, steel's not an element, it's an alloy, it's a mixture. So, not relevant right now. Okay, the only other unique thing I want to point out in the transition metals is mercury, which is Hg, right here, is a metal. It's a transition metal. It's down in this weird little section here, and it's a liquid at room temperature. So that's kind of a unique little tidbit about mercury. It's the only liquid metal. Alright, then we have one more group here, the inner transition metals. Okay, they appear separate from the rest of the table. But they're not really separate from the rest of the table. We just do that to make it easier to look at. Okay, so if we look here, it goes 56, and then it skips all the way to 72. Okay, and then we have this box here that says, well, 57 through 71 really go here. All right, so where's 57 through 71? Well, they're down here. 57 through 71. So really the periodic table should be cut right here, and those two rows at the bottom should go, and all of this should be shifted over. So the periodic table would be really, really long and skinny, especially in the middle. And so they decided to kind of chop those out and put them down here by themselves, just so we could make the periodic table fit on a page a little better. So they belong between the alkali earth metals and the transition metals. Alright, last little bit here. Many metals are found in Earth's crust, but very few are in their pure state. Okay, when we think about, okay, well, what is all of that crust of Earth made of? An ore is a substance that contains a valuable metal or mineral, but as part of compounds. Okay, so I might have a gold mine, and they're bringing up big buckets of what looks like just dirt and rocks. Doesn't look like gold. Okay, so gold ore just looks like dirt or rocks. Okay, how do they get the gold out of it? Okay, so the gold is in compounds. So if we're going to extract it from the compounds, we have to take it and perform chemical reactions on it to separate it from the things that it is chemically attached to. So that is it up for metals. I'll assign a worksheet over this, and always let me know if you need any help. Later.